Oh, okay. Yeah, I decided I might as well come back here. A lot of good places.
Which one is it?
Well, we have to have both of them.
Oh, right.
So but Julie figures if they. So maybe one of them is not.
Yeah.
She can check the other.
So everything is good to go.
Great, thank you.
Never leisure.
Oh, you know what? It's not working too.
Maybe.
I just.
Yeah, okay.
It was working the first time I had it. So I have to try again.
Making sure it's got that.
Might be because she's. It's not.
Just the main screen.
Yeah, it was working the first time we tried it. It's just-
Just try and click and see me on the screen. Excellent. Thank you. Yeah, there you move that up again for whatever reason. I think if you tap again on the screen, just to didn't focus.
Yeah.
Yeah.
Did Eleanor get back?
Okay, it's a pleasure to welcome everyone to the Adolf Grünbaum Memorial Lecture. So I'm going to say just a few words about Adolf Grünbaum, and then I'm going to introduce our speaker, Doreen Fraser. So Adolf Grünbaum was the first Andrew Mellon Professor of Philosophy at the University of Pittsburgh from 1960 till his death in 2018. He was one of the preeminent philosophers of physics of his generation and was imminent in building philosophy and philosophy of science, particularly here at Pitt. And among other things, he's the founder of the Center of Philosophy of Science and was its director till 78.
Yeah, I think that's right.
And inaugurated the annual lecture series, in which I think this is the 52nd year of that. In honor and memory of his legacy of contributions to philosophy, the Center established the annual Adolf Grünbaum Memorial Lecture. We're extremely grateful to his daughter, Barbara Grünbaum, and her family for the gift that makes this possible. And I'm delighted, and we're delighted this year to welcome back, I should say, Doreen Fraser from the University of Waterloo. Doreen studied at the University of Oxford and here in Pitt before moving to Waterloo. Her interests are extremely wide, but she's best known for her groundbreaking work in quantum field theory, where I think it's fair to say that she's one of the leading figures in the field worldwide. Among her contributions here, together with John Ehrman, she put together some of the most decisive parts of what's now seen as a fairly conclusive case that however we are to understand quantum field theory, we can't at any rate understand it as fundamentally and foremost a theory of particles. Her defense of the formal methods of axiomatic and algebraic quantum field theory as the right foundation to do the philosophy of quantum field theory remains, I think, the sort of best-in-class statement and the best defense out there of that position. And most recently, her works ranged into what you might call more kind of down and dirty, practical quantum field theory, and into the deep analogies between quantum field theory as it turns up in the apparently disparate territories of particle physics, condensed matter theory, statistical mechanics, and indeed territories beyond physics. She's provided and continues to provide a powerful series of arguments to challenge what I think is close to orthodoxy in some of the ways physicists talk about this, to the extent that these are, you know, to be loose and crude, as some of the physicists who write on this would say, these are aspects of the same thing. She's pushed the idea that these are, that the connections here are to be understood formally at the level of the mathematics and the common mathematical structures. It's wonderful to have Doreen here and to have her speak to us on the field, framework, and physics and beyond. Doreen.
Thank you, David. Thank you, David, for that nice introduction, which is actually a really appropriate setup for what I'm going to talk about today. I am, of course, delighted to be back in Pittsburgh, one of the places I think of as home. And I am really honored to be giving the Adolf Grünbaum Memorial Lecture. When I was here doing my PhD, I remember Adolf as a strong presence at all events that were going on related to, well, anything philosophical, but especially I remember him as being a strong presence at the center. And of course, I've really benefited throughout my career from the strong and important work that the center does in promoting philosophy of science everywhere in the world. All right, so today I'm going to talk about what I will label the field framework in physics. And I want to flag, I'm not only going to be talking about physics today. I think one of the reasons why what I'm going to be arguing for is important is because it has applications well beyond physics, what I'm going to be talking about. Okay, so this is my plan. There has been a lot of talk in philosophy about frameworks, and in particular how frameworks and theories and models fit together as representations in science. And one reason for that, of course, is that it's clear in contemporary physics that frameworks play a very prominent role and are really essential to the practice of doing physics. So what I'm going to do is I'm going to argue for a particular way of carving up representations that get used in physics in terms of frameworks and then also theories and models. What I'm going to start with is explaining some of my historical motivations for coming to this view of the role that the field framework plays in physics. I'm going to talk briefly about a case study that has informed my views. And then the rest of the talk will be about what I take to be the important philosophical implications for this historical work that I've done. Okay, so getting to the historical motivations, I will start with a very big picture view of how I think about the history of science. And so there is in the history of science a kind of traditional picture of how we should track scientific change, in particular change that happens at the level of theories, but it's a diachronic picture. The idea is that you should think about the domains of phenomena to which a particular theory applies, and then you kind of track the changes in the theories. Hopefully the scope of application increases as you go forward in time. But the idea in physics would be that, okay, yeah, so on the left here, we have condensed matter physics, solid state physics, many body quantum theory, however you want to describe it, going back in history. And then on the right, we have theories which are going to end with quantum field theory, but we have theories that go back into classical mechanics. So I take this to be a picture that comes from the traditional way of thinking about history of science. Also a picture that's important if you're thinking about the scientific realism, anti-realism debate, and then you get concerned about what these arrows look like and whether you have continuity across theory change of this type or not. All right, so my concern with that picture is that it becomes increasingly clear as you look at the history of recent physics that it's not going to capture everything, and it's going to leave out some of what I think of as being the most important drivers of theory change in physics in the 20th century. So what I have here are the arrows across. So what we see is you have lots of connections and points at which the arrows go in both directions. This is also important. So you have a sort of, maybe on the left, you have some sort of halt in progress in condensed matter physics. And it can happen that you have ideas that come over from particle physics that then get used in condensed matter physics, happens the other way, and actually renormalization group methods I'm going to talk about. I think it's very important in the historical development that the arrow goes in both directions, right? So from roughly from condensed matter physics to particle physics, and then from particle physics, some of the ideas go back into condensed matter physics. Okay, so this is the kind of picture of obviously, this is a big picture of historical developments in physics. And so one of my motivations for thinking about the philosophical questions I'm thinking about is looking at these historical case studies, some of which I've looked at more carefully than others, but looking at the set of historical case studies and trying to think about the implications for philosophical accounts of science and historical accounts of how theories in physics change over time as well. Okay, so now I'm going to talk about one of the case studies I've looked at. This is a brief 2-slide overview of a case study that's actually very complicated. It turns out, as per usual, the details are actually kind of important. But there will be lots of you in this room who are familiar with this case study. However, I will flag that I'm going to be approaching it from a different angle than a lot of the philosophy of physics literature, and I'll get to that later in my talk. For those of you in the room who I hope are interested in my promise that what I'm going to say is going to have implications beyond physics, there's 2 slides about this, and then I'm going to get back to talking about the broader philosophical morals and the implications of the view I have. Okay. So what I have here is a picture of one of the examples of what I take to be purely formal analogies that played a driving role in the development of this area of physics. So this was a case in which the source domain for these analogies is on the left here, and in particular, I have a ferromagnet on the bottom. So the ferromagnet is standing in for a class of phenomena in condensed matter physics, in which the ferromagnet undergoes phase transitions, some of which can include becoming spontaneously magnetized. So under the right circumstances, it can become magnetized even when there's no external magnetic field. This was the kind of phenomena that was difficult to model. One of the models that ended up being adequate for this case is what's known as the Ising model. For this particular example that I'm going to be going into, in fact, the classical Ising model is really what you need. So here's a cartoon diagram of what the model, the starting point for the model, what it looks like that you use to account for this kind of phenomena. And so what's important to me is that this is a classical model. So you have a spin field, which is defined, these little points you can think of as atoms on a lattice. And this is our representation of this metal bar, and you can make it infinitely long if you want. In fact, you might need to, depending on what you're trying to do. And so what's important here is looking at the correlation functions between the values of the fields and spin fields at different points. This is going to help us to solve a problem we have over on the right-hand side, theoretically speaking. So now what I'm talking about is work that was done by Ken Wilson and collaborators in the early to mid 1970s. And so the insight was, if you have, so this is not exactly as David was explaining, this is not exactly what I don't think this is what a quantum field looks like. This is a sort of model maybe, but anyway, it's supposed to be suggestive of, look, this is sort of formally like this thing over here. And so if you can formally adopt a model that's somewhat similar, then maybe you can use somewhat similar methods of solving this big theoretical problem over here to solve the theoretical problem we have over here. Okay, so the theoretical problem over here, this is a picture of the one of the detectors at CERN. You want to have a theory which can make predictions of like what happens when you scatter particles off of one another, which is a relatively low energy phenomena. So what you need is you need to start from a relatively high energy theory, and then you need to somehow figure out how to get predictions out of that theory. It involves renormalization, and what turned out to be the useful insight here is that if you induce a mathematical there's a mathematical transformation which gets you from the model on the left to the problem you want to solve on the right. It involves using renormalization group scaling transformations on both sides, taking limits on both sides, and then you get the kind of predictions you want on the right. Okay, so that's the very high level view. There's 2 references to 2 papers which go into all of the details that probably anyone would ever want to know about this. But what I want to stress about this example are 2 features of it. One is that it's a purely formal analogy, by which I take it to mean that it's based on mathematics, and the reason we have for setting up the analogical mappings between the left-hand column and the right-hand column is that mathematically these elements on the left-hand side and right-hand side play formally similar roles. Okay, so you can tell we have fields on both sides. Obviously, that's going to be important to my field framework story. The fields are over something, some x's, and then correlation functions are also going to be important on both sides. We're going to have these limits. We're going to have the renormalization group transformations I haven't even included in this list. But furthermore, by saying that they're purely formal, I mean that there are clearly physical connections between the representations on the 2 sides. The physical relationships, similarities, do not come into setting up these analogies. And in fact, the analogical mappings are bridge across physical dissimilarities of a really fundamental sort. Okay, so read the papers if you want to hear a lot about what the physical disanalogies are. But one quick way of seeing it is on the left-hand side, you have spin fields, which are defined over space. On the right-hand side, you have a relativistic quantum field theory, over which your degrees of freedom are space-time degrees of freedom. So essentially what you're doing is you're mapping space to space-time in the course of setting up this mathematical analogy. So then this very quickly shows you that the causal structure that you have, that's the explanatory target in particular on the condensed matter side, does not map over to causal structure of any kind on the quantum field theory side, which is not to say there isn't causal structure on the quantum field theory side. It's to say that these analogies do not map causal structure to causal structure. They do not map modal structure to the same sort of modal structure on the other side. So that's the sense in which I'm saying that they are purely formal analogies driven by the mathematics without accompanying physical analogies to underlie them. Okay. So back to my motivations here. So I've just said I carefully looked at this case study. As David said, I looked at other case studies. And it seems to me, if you look at the historical record, purely formal analogies of this type have played an important role in successful episodes of theory development in physics. This, on the surface, seems like it's problematic because the specter of 2 miracles, which are well known in the philosophy of science, seems to immediately arise. So the question then would be, I've just said these purely formal analogies are successful methods to make these new discoveries. First question, if you subscribe to the no miracles argument, then success is to be explained by getting something right about the world. So if I've just said that what you've gotten right is math, then does that mean we should all be Pythagoreans? Does that mean that we should think that the world is actually mathematics? So we've literally gotten the mathematics right when we get these formal analogies that are successfully driving new physical theories. Second miracle that comes in as well in this case is Wigner's miracle of the applicability of mathematics. So we've been successful in this case. So does that mean that there's some sort of pre-established harmony between the pure math that we're using in the world? So my thesis, of course, is that this is only an apparent problem. And I think that the successful use of purely formal analogies is explicable in purely naturalistic terms, right? Naturalistically acceptable terms. So there's going to be no pre-established harmony in my account, and there's going to be no Pythagoreanism in my account. So how is that going to work? So here's my explanation of why purely formal analogies are useful in these cases. So this is where the field framework is going to come in. So why is it that the formal analogies that Kenneth Wilson used in this case to map between the condensed matter application of renormalization group methods allowed him to transfer those methods over to particle physics? Well, it's because what was underlying the formal analogies was we assigned degrees of freedom to points using fields, right, mathematical fields. There are both cases in which there were fluctuations in the field values of some type, and then this meant that the quantities that were theoretically interesting to us and also phenomenologically interesting for making predictions were correlations among the fluctuating field values at different points. And then once you have this mathematical model in place, then it seems like it's a good idea to look at general mathematical strategies for solving problems of this general type, right? So if you find a mathematical strategy that works in condensed matter physics, then it seems like if you set your model up in a mathematically similar way in quantum field theory, try the same strategy and see if it works over there. Of course, there's no guarantees, but try it. Okay, so that was the field framework. Let's fill in a little bit more about how it works in this example. So what's happening is this abstract, what I'm going to call an abstract field framework, has two different concrete applications. And so in the Ising model, on the Ising model side, X is going to be interpreted physically as a spatial lattice. And then S of X is the spin field. Q of T, we're going to interpret X as space-time. Phi of X is the quantum field. The fluctuations are then going to lead us to care about correlations of different types. So in statistical mechanics, it's the correlation functions that are really important. In QFT, it's going to be the vacuum expectation values of the propagators. And then, of course, RG methods are at the heart of the whole thing, right? That's the particular general method that is going to be exported from one side to the other. Okay, so here's my explanation, and I hope that I didn't invoke Pythagoreanism or any kind of pre-established harmony between pure mathematics and physics. So the explanation is simply that there is an abstract field framework that's playing an important role behind this kind of example, and it has different concrete applications in these two models. So to fill that in a little bit, to give people a bit more of an idea of what I have in mind by a field framework, everything that's in black here we've already talked about. There are other mathematical features, which are kinds of like mathematical representations strategies you can use. So there's representational ingredients you can add to the field framework. So often privileged states are going to be important. And so, for example, now this is not abstract anymore. This is a concrete example, interpretation. So equilibrium states or vacuum states are going to be important. And this will come up later, spontaneous symmetry breaking and the symmetries that get encoded in Lagrangian. This is another really important component of a representational strategy you use, and sometimes it's kind of comes into problem solving as well. The field framework makes available. Okay. So I stress this is a partial list. I think once you start thinking about it, there's lots of other things you can add to the list. All right, so there's a lot going on in this diagram, but this diagram sort of encodes the talk. So I'll go through it and explain it, and then explain the thesis that I'm going to be arguing for the rest of the talk. Okay, so what I have here is a way of carving up representations that get used in physics into different levels. And the levels are levels of frameworks, theories, and models. So starting at the top is what we were just talking about, is the field framework. So that at this top yellow level is what I'm going to call an abstract framework. So there's a lot of problems with terminology here. I'm going to try to be clear about how I'm using this terminology, but of course, people use this terminology in different ways. So what do I mean by abstract? So as you go down the diagram here, you have lesser degrees of abstractness, which is going to mean that as you go down these levels of representation, you're adding concrete physical interpretation. So what we just saw was the abstract field framework, and I've included the examples of what I'm calling theories here. Again, you can call them models if you want, doesn't matter to me. But this level is the level I'm picking out as the theory level. So the 5.4 quantum field theory was the concrete theory that was being constructed in the first instance by Wilson and Kogut in their paper. Then they generalized this method to other types of interactions, but that was the first sort of interaction they constructed. And then on the other side, we have the statistical mechanical Ising model. I've included, to give you an idea of what I'm talking about, a bunch of other examples, which are examples of what I take to be theories in particle physics, other examples of from statistical mechanics. I've stuck to sort of standard examples from particle physics, and then the types of theories you run into if you're thinking hard about collective phenomena in statistical mechanics. But I take it that this is, you could expand this significantly and have a lot more theories on that level. Okay, so then what happens in between? Because I skipped a level, right? So what happens in between is what I'm calling the concrete framework level. And so what I have in mind here as examples are, on the left-hand side, I have quantum field theory, which, to clarify, is what I take to be the theoretic, sometimes this is called the theoretical framework, right? The theoretical framework that lies behind particle physics. So the R here stands for relativity. So special relativity, I'm not going to talk about general relativity, I'm not going to talk about quantum gravity much. Just let's stick to special relativity. And so this is relativistic quantum field theory on this side. And then on the other side, I have statistical mechanics. And typically in the historical examples I've looked at, this side, it's actually kind of important that it's not relativistic. I'm going to talk more about that on the next slide, or slide after that. Okay, so this concrete framework level, I think, is very important to include in this diagram, because I have the field framework here at the top, which is abstract. So if the field framework says fields are mathematical ways of representing degrees of freedom spread across something, space or space-time. As soon as you specify what the fields are fields of, and you specify, for instance, down here, whether space-time over here and space over here, then you've added some concrete physical interpretation, and then that's where you start to have to beware of this black dotted line. So the black dotted line is a line that you cannot cross if you want to use analogies. You need to be careful not to take the physical interpretation from this side over to this side, because you've defined things differently, right? You've interpreted this abstract framework differently on the two sides. So you need to be aware of that. So this black line is supposed to be a semi-permeable membrane. It's a reminder that you can, formal analogies can quite happily go back and forth in the two directions, but you have to be very careful. If you're trying to take some physical conclusion, explanation, causal structure, you've developed over here, and move it over to the other side. I've also put over here, I'm not going to talk much about this, but I think this will be interesting to lots of people in the room, that if you look at the examples, one of the things that comes out on the quantum field theory side is often it's a space-time representation. You're trying to deal with closed systems, and you're trying to deal with evolutionary models or dynamical explanations. And often on the other side, you have open systems, and you are most naturally in a category where you're intervening on them from the outside. So you have interventionist types of causal explanations. And actually, it turns out, I'm not going to talk about that, but to understand why formal analogies are useful, that's actually kind of important, because often there's lots you can do over here and lots of experiments you can do, much harder over here just because of the way things are set up causally, explanatorily. So actually the physical disanalogies help you in using the formal analogies rather than block you, which is kind of interesting. Okay, but I promised I would not talk too much about formal analogies. I'm gonna stick to what I'm supposed to be talking about here. Okay, so I didn't talk about this level, but I wanted to make it clear that you can keep going down into a lesser and lesser degrees of abstractness. So here are some examples of models, I'm calling them, but they obviously have, you add more concrete physical interpretation as you go down. There's greater specification of what kinds of systems you're dealing with. And then you can keep going down. There's probably phenomenological models below this. I think you can kind of keep going up as well, right? So what I have in mind by this field framework is it's a kind of level of applied mathematics, right? So you represent using fields to represent degrees of freedom. If you think about what pure mathematicians are doing, maybe they're like not even thinking about that much physically, right? So perhaps you can keep going up in terms of greater levels of abstractness as well. Okay. One thing I should also be clear about is I'm being neutral here with regard to how exactly you formulate your QFT and how exactly you formulate your statistical mechanical theory. Doesn't matter to me at this point whether you pick your favorite axiomatization or if you want to use some sort of textbook version, that's fine with me too. I'm being neutral about that. The important thing to me is this level is an important level to take into account when we're thinking about how physics works. Okay, that's the same diagram, so don't worry if you can't read it anymore. It's just reminding you that that diagram is there. Okay, so as I was stressing, lesser degrees of abstractness means that the concrete details of physical interpretation are added. That's going to have the implication that as you go down in my diagram, there's typically going to be decreased scope of applicability because as you add more and more details of physical interpretation, then the systems to which your representation applies is obviously going to get smaller as a class, right? However, this point can be kind of confusing. And so one of the virtues, I think, of the way I have of carving up frameworks, theories, and models, where you keep this field framework at the top and work down from there, is it's a clear manifestation that there's a difference between what I'm calling formal generalization and physical unification. Again, lots of problems with terminology and people using the same terminology. I'll explain clearly, hopefully, what I mean by these terms. Okay, so formal generalization means going up in levels of abstractness here. And so if you're formally generalizing, you're, say, going from a concrete framework to an abstract framework. And so you're developing frameworks with increasing levels of abstractness, or whatever, going to theories to concrete frameworks. This is not the same thing as trying to achieve physical unification. Okay, so what do I mean by physical unification? I think using it in the way it's usually used in the philosophy of science, philosophy of physics literature. So physical unification means to develop theories or concrete frameworks that integrate theories or concrete frameworks with fixed physical interpretation and different scopes of applicability. Okay, so what was Newton doing? Newton was trying to affect a physical unification between terrestrial physics and cosmological physics. That involved taking theories, concrete frameworks, which were applicable to two different domains of phenomena. They were interpreted. That's the important point here. right? That the formally generalizing as you go farther up, you get to the field framework level. Figuring out a new, more general mathematical framework to use does not automatically entail that you're physically unifying anything at all, right? Because you have to pay attention to that black divided line, right? So let me give you some examples to contrast this diagram with, to give you some examples of what you might be thinking about if you're thinking about physical unification, which I think is an important goal. So let me stress at this point that what I'm trying to argue for in this talk is that we need to use what I'm calling the abstract field framework in order to think about how physics works. But I'm not arguing that this is the only way to carve up representations, right? There are other ways of carving up representations, which I'm about to show you right now, which are the right ways of thinking about things, depending on what kinds of philosophical issues you are thinking about, and also what kind your goals are in physics. Okay, so here, for contrast, is a possible physical unification scenario. I'm going to give you two of them. Right? So this is something which I think, if you start thinking a little bit about effective field theory perspectives in physics, you might be led to. Let me emphasize, I'm not endorsing this even in the weakest sense of possibility. There's lots of details which are important here. What I want to present as a contrast is the green lines are different than my lines that I had on my previous diagram, right? So what is happening here is I've fixed a scale, by which I mean I've fixed a physical interpretation for scale. I picked energy. So at the top we have low energy. And I don't care here whether you think in terms of models or concrete frameworks or whatever, right? As long as it's interpreted. So you might think that at the top you have at the low energy some sort of representation of superconductors. So at some level, you're going to have maybe that goes down into into the standard model. Keep going up to higher energies. There's maybe some beyond the standard model theory we don't have yet, which is down there. Okay, here's my one reference to quantum gravity. So that you go down to quantum gravity, keep going, maybe, who knows, right? The idea here is that you would be affecting some physical unification if you were able to do this. So this is the way that you tend to structure relationships if you're interested in the important philosophical issues of reduction or emergence. So that's going to be a question about how you interpret these lines. Perhaps we need more lines, as Bob suggests, coming in from the sides. This is not the diagram I had up, and so the difference is everything here has some fixed physical interpretation, and then you're thinking about how they relate, say, to different scales. So I wanted to say that this is an important way to structure relationships between different theories or frameworks if you're interested in these questions. But I also want to put a plug for a paper that Adam and I recently wrote, which I think makes it clear that the abstract field framework I just had up is also important for thinking about effective field theories and how they work. Here's another way you might think of doing physical unification in contrast to my favorite diagram. It's to just fix on what I had as the concrete framework level and introduce a unified concrete framework, which is going to include quantum field theory and statistical mechanics. What I want to emphasize is that this is a project, however, because of the black line in there, right? Because the interpretations of, so the field framework is not going to give you this for free because you've interpreted what the fields are differently in the two cases on the quantum field theory side and the statistical mechanics side. So figuring out what the purple box is a project which involves erasing that line. You're going to want some sort of relativistic statistical mechanics or thermodynamics that applies to field theories or something like that. Okay, so that's the kind of project I have in mind as another way in which you could go about unifying. So I think finite temperature field theory is an example of a project in that vein. Okay. Wait for time here. All right, so here is what I want to argue in the rest of the talk. So this diagram represents a way of carving up frameworks and theories and models in physics. And what's distinctive about it is that it has the field framework at the top and everything comes down from that. And the field framework is an abstract level of mathematical representation. You might want to think of it as a level of applied mathematical representation sitting at the top. So what I want to argue is that there are advantages to carving up the space of representations in contemporary physics in this way. And so as part of that thesis, what I'm really interested in is what this field framework level as an abstract representation, what role it's serving in physics. Okay, so especially as you go down to this concrete level, but then also in theory or model construction. There's been a lot of really good work done in philosophy of physics and philosophy of science in recent times on what might be thought of as the low, if you want to carve things up this way, the lower echelons of this diagram, right? So there's a huge literature of models in philosophy of science. And so I take it that that is working out some of the issues that get involved if you're thinking about how to apply models in realistic circumstances, or what kinds of representations you use down at this level. There's also two of the projects that I think are close to mine, is of course Mark Wilson's work on uncooperativeness and physics avoidance, looks closely at applied mathematical issues that you run into and the obstacles to trying to work at the level, the lower levels of the diagram. And similarly, Laura Ritchie's work looks at, if you pick RQFT or statistical mechanics, how exactly does that, as a concrete framework, relate to different models that get applied for representing different types of phenomena. Okay, so my thesis, in contrast to those kinds of projects, is to say, look, let's actually it's important to look up here and to see what's and to look and see what's happening at the abstract level as well. Okay, so that's what I'm going to be arguing for. One reason I've already given you for this way of carving things up being important is the historical one, that I think you can actually see it being done in historical practice. But I'm going to set that one aside and focus on the more philosophical arguments for the rest of the talk about what the advantages are for this way of seeing things. There's also, I think, a kind of practical physics motivation, right? So it's important, I think, for philosophy of physics, philosophy of science, to be engaged with the kinds of issues and decisions that physicists are making right now about how to do physics. So one way in which this question impacts practice in physics is, I think by looking at these recent historical case studies, we can see that purely formal analogies have in fact been really useful as a heuristic device for constructing new models in physics. So there's lots of questions about what to do to develop new theories and models in physics right now. I think that physicists should be encouraged to think whether formal analogies might be the right tool, and shouldn't always think that there needs to be a physical analogy behind their strategy for developing a new theory in quantum gravity, say. Okay, so that's the final point, the final thing at the bottom. So I think also there's a formal generalization, if we're thinking about this field framework level, as we'll see, is a plausible strategy for making progress in science. Okay, so I have three advantages I'm going to talk about. The first advantage, and maybe this is just trying to really emphasize this important philosophical point is, I think it's a huge advantage that formal generalization of this type does not entail physical unification, in that if you are looking for a more general abstract framework at the highest levels, that you're not automatically going to be physically unifying different domains. So one reason that this is important to distinguish is because it allows you to articulate clearly research questions that apply to formal generalization, but do not apply if your goal is physical unification. Okay, so disentangling research questions is useful. So here are some examples of some research questions which I think pertain to formal generalization, trying to develop more abstract frameworks, and are not directly related to physical unification. Okay, so first example, is it possible to develop a unified mathematical formalism for renormalization group methods? So at present, renormalization group methods are this sort of grab bag of mathematical techniques that bear a certain family resemblance to one another. But you might wonder, once you've thought of things in this way, so calculus, if you're learning calculus as an undergrad, you might take an applied math course, right? And so physicists might be in the same classroom as biologists, et cetera, et cetera. If you're learning renormalization group methods, probably you're in grad school, but you would be studying a textbook that's called Condensed Matter Physics for Quantum Field Theorists, or Quantum Field Theory or Particle Physics for Condensed Matter Physicists. Okay, so you might think, okay, well, like, first of all, maybe we could like teach renormalization group methods to undergrads, but in any case, the idea is there an analog of a calculus textbook for renormalization group methods? Okay, that's, I think, an interesting research question. I think the follow-up question is that even desirable? I'm skeptical about whether it's possible, but we can talk about that more later. Stating the question is an important thing. Okay, here we get into thinking about axiomatization. So I think thinking about generalizing in this way forces you to think about the role of axiomatization in physics, and maybe in mathematics too. Do axiomatizations of the concrete frameworks, algebraic QFT, for example, or algebraic quantum statistical mechanics, if we look at those, do they suggest additional applied mathematical techniques that might be transferable? Okay, so this is an example of an actual in mathematical physics research program, right? Because model construction in both cases is really hard. This is a sort of, so if you find in sort of rigorous mathematics, a mathematical technique that works on one side, try to find a way to map it to the other side, because you might be saving yourself a lot of mathematical trouble. And finally, are there modifications we can make at the abstract framework level that could lead to progress in physics? So we have problems trying to formulate new theories. In broad strokes terms, are those because we don't have the right math, or are they because we don't have the right physics? So clearly it's a problem, probably both. But I think one virtue of thinking in terms of abstract frameworks is you can kind of start to disentangle those questions, right? And think of different research projects. Like pluralism is obviously the right way to go here. Different research projects should pursue different strategies. Thinking about the field framework by itself as instead of applied mathematical representational strategies and techniques for solving problems might lead to progress in applied mathematics, which might make some of the problems go away. Maybe it also lets us think harder about what we need to do in terms of getting new physics to solve problems which are obstacles to getting better theories. So the second point I think that's important for philosophy of science is the conceptual clarity point. So this is the black line, and minding the black line that comes in between, in particular, condensed matter physics representations, I think, and relativistic QFT interpretations. So you can't automatically export a physical interpretation from one side of the membrane to the other, right? And so here I think is one example of that moral, and this is where spontaneous symmetry breaking comes in. As John Urban has argued, as long as, and I won't have enough time to explain spontaneous symmetry breaking to set this up properly, but the punchline is that as long as the system of interest is closed, there's no temporal evolution involved in spontaneous symmetry breaking in QFT, since every physically relevant state is asymmetric with respect to the symmetry of the Lagrangian. So this is a realization that is the product of a lot of careful looking at quantum field theory and spontaneous symmetry breaking, a lot of careful investigation of what's going on in spontaneous symmetry breaking and condensed matter physics examples like superconductors. But one of the virtues, I think, of having the abstract field framework in view is that it flags that we should expect these kinds of observations or philosophical conclusions where we're recognizing the important physical differences between interpretations of spontaneous symmetry breaking in this case in the two sides of the divide. So I don't think just like putting the abstract field framework on top is going to solve everybody's problems automatically, but at least it keeps us wary of taking our physical interpretations that are often very much more clear in condensed matter systems and just taking them over to particle physics uncritically. And finally, I am going to talk about something other than physics here, and here's where it comes in. So the abstract field framework is very abstract, and that's one of its virtues insofar as it has applications that go beyond physics, right? So a field is just a mathematical way of representing degrees of freedom spread across, say, space or something, right? So and then you can interpret it in different ways. Not only can you give that framework different physical interpretations, you can give it different biological interpretations. In this case, you can give it different economical interpretations. That's the right way of putting it, economics interpretations, I don't know. But the idea is that your dots, your points, could be traders, right, in a market scenario. And then you can start thinking about field models of stock market crashes, say. So here I'm going to point to some excellent work that's being done in looking at econophysics modeling that's being done, in particular by Patricia Palacios, and also this paper with Jim Weatherall. And so this is from their analysis, but I think it's a nice illustration of what the field framework can help you do if you are thinking beyond physics. So think about using those fields to represent economic degrees of freedom, like your traders. Then you can try, as what's known as the JLS model does, try to do, use renormalization group methods to try to solve. If you have a bunch of traders and you're thinking about stock market crashes as coming about because you have some sort of self-organized activity in markets, that's sounding a little bit like collective, the critical phenomena, right, and collective behavior that we see in condensed matter physics systems. But that seems like, on the one hand, a fruitful applied mathematical strategy, because we've, as in physics, right, if something works in one case and something looks like you can model it in a mathematically similar way, why not try the same mathematical strategy? Maybe it will not work, but it seems like it's at least worth trying. However, the same kind of caveat holds, right? That we're not, I mean, obviously, I think one of the advantages is people might not get so hung up about whether traders are like, whether, so obviously spins, degrees of freedom attached to atoms are not sentient. That's an important difference between traders, but there's lots of differences. In the first instance, you can at least try the mathematical techniques, see if they work, but then what you get out at the end is going to depend on the interpretation you give the mathematics, right? So this is the excellent work that's being done right now. So we shouldn't assume that the results have the same concrete interpretation, even if you can use the same mathematical modeling strategies. So in the stock market case, you end up with sort of context-specific explananda, which differ in interesting ways from the types of why questions you're asking in condensed matter physics, such as why do stock market crashes occur at all? And it seems like there's at least the potential for interventionist causal explanations being relevant and possible in those cases. I think that's the part that's pending further study in this work. All right, so I assume I'm running out of time, so let me wrap up here. So what I've tried to first motivate and then provide some arguments for in this talk is that we should carve up frameworks and theories and models in physics in this particular way, which is to say that if we don't think of things this way, I think we're missing important aspects of how physics works that we need to take into account. I'm not saying that there are no other ways of carving up representations in physics, even into frameworks and theories and models, which would serve different purposes in philosophy and serve different purposes in physics. But I think this is one that we need to keep in our collection of conceptual schemes to use. One of the points I've tried to stress is that formal generalization, which means trying to go up and come up with especially frameworks that are more abstract than we have right now, is not going to entail physical unification automatically, in the sense of having we don't automatically get a new physical theory, which applies to more a larger domain of phenomena than we did before. And then I talked about 3 advantages that I think the abstract field framework has. First of all, it allows us to distinguish goals of formal generalization and physical unification, which allows us to clearly articulate different kinds of research questions. Second, conceptual clarity is an advantage. Once we have that black line in there, hopefully we're reminded that we can't automatically be moving physical interpretation back and forth. We need to take care in doing that. And thirdly, I think that this is a starting point for critically evaluating applied mathematical methods that have proven to be successful in physics and what it looks like when we try to apply them beyond physics, such as in econophysics. Thanks.
Okay, we'll take just a short break and then return for questions in, say, 5 minutes.
Yes, I did. Yeah.
I recognize it, I'm sorry.
Yeah, you were supposed to be a bit of time in later.
Yeah, well, right, if we,
Wonderful.
expediting it. So
Sorry, what?
they're expediting it, so we should help them do it.
Yes,
Right,
I know.
Yeah, well, no, it's wonderful.
Yeah.
No, thank you for your.
I came on late
Yeah.
I think I felt the process.
Okay, that's what I.
Sounds like you're interested on your university.
All right, good.
Yeah. You want to disagree with anything you said? It sounds perfectly-
No, you were saying earlier, the last talk you heard me give.
Oh, yeah. No, the last talk you gave, like, was that scales fell from my eyes experience, because I could never figure out how fluctuations in statistical physics were mapping onto something that was going on. And you gave the mapping. And it was, that's how. No, but here, you told me something.
Yeah, I will send.
Who the hell's going on? Sometimes things have to be said. I'm saying.
And when I get home.
Thanks, John.
I don't know, am I digging a hole for myself?
I was teasing you, because you just did that.
Okay, yeah. No.
Are we sweeping up Norton eye scales off the floor again, or not?
No, he said this talk wasn't as good as the last one he saw me give.
No. Here's the problem. She gave, it was a PSA book. It's one of the best books I remember in my life. And I told her so. And so now she's complaining
Well,
that I'm not.
you know. Come on, if you peaks, you can have another peak. We know there's rough, rough landscapes out
Getting
there.
out of here before
I'm
I.
gonna give you a hug. I've had a kind of complicated week, so I'm gonna go home. I have 2 dogs who both had surgery.
Oh, that's too bad. Are they okay now?
Oh, yeah, I think. Well, one just is a new dog who got castrated. We talk about that.
Okay.
Very touchy.
I've had pets.
No, really, Clark Limor, you can't tell him this because it's just like, I don't know what it is, but I just don't even want to deal with it.
Okay.
It's really great to see you, and I take it we'll see you back. here
I'm
in
gonna be
November,
back, yes.
And we'll have we're gonna.
John
have
is
the-
coming too.
Oh, wonderful. You know, we're doing the 50th.
Yeah, we'll be
So
there.
I was looking for photos, so I have a picture of you with your first.
Oh,
I might
Arthur's
send it
gonna
to you.
turn 18 next week.
I was gonna ask, but I was afraid.
So I was looking for pictures and I had like tiny ones of the 10 for 10
I got all the
already.
10
I thought, I assumed you would.
I just uploaded those. So
And I have other ones I think I got from Holly because they're small and she
Okay,
was the
Holly's gonna do
photographer.
some.
Yeah, okay.
The thing about the psychologists, I think that probably the last time I actually saw your children, they were about the same age as mine are now, and you never realize
Yeah.
people's children grow up.
Yeah.
My mental map is that you have still the same
Small.
age. I know. And you intellectually, that doesn't sound that ridiculously wrong.
Yeah, it's hard to update without more content.
Yeah.
Anyway, I'm gonna let you go.
Yes,
and-
no,
and
I hope
do
you're,
that,
you're
but,
absolutely fine.
I really liked your talk. I see a lot of things in it that are connected with.
Yeah, good. Well, I will be back.
Yes.
So and I'm writing a book about this. So.
Oh, excellent. Well, that's good.
Yeah.
Okay, well, thank you. Yeah.
My one sentence versions, I have to find the keeping as I don't agree with the core.
Yeah, well, I don't know. So, and this is where because I mean, obviously, there's a perspective which pluralism is the way to go, but then it's the more defined question of for what purposes do you use it, right? So.
And we'll get to the next extension, so I mentioned this reception.
Yeah, yeah.
I mean, it's really like 5 minutes,
I
right?
got it. Yeah, well, but I have to have it.
I asked you a-
Because I'll be back.
Certainly, yeah. Do you want me to put my mask on?
No. Earlier in the talk, you made a statement about.
Yeah.
Which I realized at the time, I'm like.
Yeah.
So was that the same point as later on?
No, it's a kind of different point.
Okay.
That, in fact, it's a kind of stronger point, right? That,
I have an
So-
actual question, which I'd be happy to hear the answer to.
yeah.
Okay, great. The whole-
Yeah, so usually, so the analogies literature usually takes it that in order for an analogy to be useful in physics, it has to be a physical analogy. And so I'm arguing contrary to that. There's cases in which it's just not that. Yeah. Anyway, happy to talk to you about that.
Okay. Questions. So I saw, so let's have Siddharth first, then we'll go Kabir, Sabrina, Chris.
Sorry, am I first?
Yep, Kabir.
Yeah, thank you. That was very useful. So I wanted to ask you and maybe get a little bit more clarification on, the degree to which physical unification and formal generalization are different. And to sort of press on that distinction a little bit, it often seems to me that physical interpretation does not follow from physical unification. So, if you have a fluid, you can do a molecular dynamical model where the physical interpretation is of molecules moving around. And, at the fluid dynamical model, the physical interpretation is of velocity fields, right? So there seems to be a physical unification there. We assume that the fluid dynamical model is explained by the molecular dynamical model, but the interpretation changes as you shift the level, right? And and from the other side, I feel like sometimes formal generalizations do have kind of deep physical explanations, right? So for example, if you ask why do we always use second order differential equations in physics, at least one plausible explanation is this Ostrom-Brodowski instability or something like that. Right? So anyway, it seems to me that the distinction is not very sharp. Right? Is that okay on your
In a way, it's okay, but let me explain how it's not okay because going back to my favorite picture, if you think about what's happening at the top, I've included some important levels here, but there's degrees here, right? So you can put in lots of other levels in between if you want, right? I think that when you think about fields, it's like thinking about degrees of freedom seems to be, I think, as vague as you can get, right? I think if you take away the idea that you're representing anything at all, this is why I was thinking that if you go more abstract than that, you do pure math, right? But the question you're asking is the other direction, right? So if you go down in level of concreteness, then at what point do you get physics, right? Like at what point do you have a physical theory and not just an applied mathematical abstract thing, model, right, or something, which could be filled in different ways. So that's kind of why I put field framework above my line, right? And I think anything you add onto that, then it's going to put you in this situation where you are going to have you could go different ways, right? Depending on how you try to interpret the elements of your mathematical model more concretely. The first thing you said was about whether at different levels you can have different representations of what the base level is or something like that, right? Or and I think that's right. And this is intentionally vague, this diagram, and there's lots of ways in which you can disagree with. I mean, I haven't put anything very specific up here, but there's just so many different ways to go here. But I think that would fit in here. The important thing for me is, in order to even talk that way, you need to fix the scale over here, right? It can't be either energy or distance or whatever, right? It has to be you have to order things in a particular way. And that gets important when you're thinking about how renormalization methods work in particular.
Could you maybe put you back as the list?
Yeah.
Because I have a couple of questions.
Yeah, sure. And anyone else who's got questions, keep your hand. I'm still taking lists, so yeah.
Could I maybe just ask, because I think the two problems you mentioned, the second one was the vagueness kind of worry about the effectiveness of mathematics. But I mean, could you maybe recapitulate your answer? Because I thought, oh well, you say that there's this abstract field and it does all the job. That doesn't tell me why mathematics is able to represent such this diverse physical phenomena.
Okay. So the bigger question lying in the background here is what exactly the problem is supposed to be. And I think that actually, I didn't say anything about that. And that actually needs a lot more work than Victor does. In fact, he's probably going to do 3 problems, right? So let's set that part aside. So what I was saying with the abstract field level, kind of applied mathematical model, is that because it's leaving so much into future, like when you apply it, you have to give a lot more concrete physical, you have to give a concrete physical interpretation in order to apply it, right? What I had in mind here is the sort of miraculousness that somehow pure mathematicians went away, right? And they came up with all this math and they weren't thinking about the world at all. And then lo and behold, they turn around and it turns out to be applicable to the world. So is that because, there's some, the way humans think about the world and do mathematics is, this goes back to hundreds of years ago, right? Is there a pre-established harmony between our mathematics, what mathematics have come up with and the way the world is? I think that's not the case. And I don't think that comes, I think by adding the levels of physical interpretation, and so pure math would be like a higher level than the applied field framework level.
Right, yeah, but I thought the worry was something like, oh, let's take this analogy, right? I have flour. I could make pies and cakes and pasta and so many things out of flour. Of course, I can make so many things out of flour because flour is it's very good, you can make lots of string out of flowers. But that's, maybe that's not the worry, right? The worry is why is, what is in this flower that makes it happen that I can make pasta and cake and pies out of it. Flour is a neutral substance, so that's why it has diverse applications. But why are these diverse applications unable to be made out of flour? So that was.
So I think that sounds to be more like number one, right? That sounds to me more like, you know, if flour is useful in all these circumstances, why wouldn't it then be the case that it's really like that? Well, how do we explain why we're successful, right? And then this gets back to the realism kind of worry. But so in general, let me say this, maybe this will help. That I think that like when you look at so I don't think it makes sense to say I'm a realist about the abstract field framework, right? Like I'm a scientific realist about the abstract field framework. So it does get all these applications in physics, but what would it mean to say, I think the abstract field framework gets the world approximately right? Because it doesn't describe the world at all. You have to get down to the concrete framework level before you're describing the world at all.
Thank you very much for your help. And how this relate to the Fraser Lowe's debate about algebraic approach and field theory. One specific argument I was thinking in defense of the effective field is that the problem that's kind of swept away by renormalization is due to the unknown underlying physics that into gravity. Would you say that because based on this picture, would you say that this satisfying answer because if the problem exists in the abstract framework level, then it won't be solved by developing more concrete physical theories. We have better.
Yeah, so I don't have quantum gravity on here, right?
Yeah.
And so the starting point thinking about effective field theories means thinking about some sort of hierarchy of theories which are indexed to different scales. So then that's going to get you into the other picture that I had, right? This kind of picture. And then this is where quantum gravity shows up down here, right? So as far as what that has to do with the why pursuing axiomatic approaches to quantum field theory might be a useful thing to do conceptually. Oh, actually, well, I was going to go to another slide, but this is kind of a different point, I guess. But so this is where the axiomatizations came in, right? And so I think if you're like focused on what's happening at the more abstract level, then questions about what mathematical framework is going to be the most useful in many different pragmatic senses are going to come in. And so I think that's where thinking harder about the type of math you're using is going to be relevant. Right. So I think so I'm saying, let's focus on the top. And that's related to thinking that there's insights that can be gained by thinking about those types of axiomatizations that are more mathematically rigorous.
If one thinks that we should approach QFT from the algebraic perspective, then we should also approach this matter through.
Well, it depends on what you're trying to do, right? So it's more pragmatic than that. I mean, it depends on what your purpose you have in mind is, right? So I'm arguing here that there are purposes for which I think that's a useful thing to do. Right? I'm trying to give you some examples here and some context. But I also said, look, I'm not dogmatic about this. I think, I pointed to this other paper that Adam and I have written on EFTs as well, right? So I think that thinking about how this kind of scale by scale representation works and what it's telling us about physical connections between different levels is a different kind of question, which is also an important question to ask, but it's a different kind of question.
Thank you. So I'm trying to see I'm thinking through kind of a particular scenario. And ultimately, what I'm getting at here is how committed are you? How committed is this representation of things, in fact, to either an axiomatic presentation or something different? So I can think of a number of scenarios. In the axiomatic framework, it seems to work nicely, right? As you kind of go down, you're adding more interpretive principles, more structure, or whatever you want to call it. I could also see, though, say you get down to one of these bottom scenarios now, and you've added kind of a bunch of extra stuff there on top of just the framework. And now what you say is, actually, one of the assumptions I took on pretty early. Right now, I kind of don't want to commit myself to that. Does that pull you out of the framework? This happens fairly regularly.
So is this a question about like idealization? Is that what you have in
Well,
mind? or-
idealization is one, right? But I mean, there are points at which during calculations that we want to say, you know, we say up front in specifying model, look, it's conquering variance. And then we get to a certain step in the calculation and say, actually, we're not. So I'm not coming up with a good example, but I'm thinking of the kind of looping structure that you might have here.
So this is maybe not exactly to your question, but it might help a little bit. So one of the things that I find really interesting about the types of examples I've been looking at is the skipping of that level you were just talking about, right? In a way, right? So, like you have the field framework standing in the background, it's giving you a pointer to some of the mathematical and formal analogies between not QFT writ large and statistical mechanics writ large, but what I'm calling theories, or maybe think of them as models here, right? So what is Wilson really doing? He's looking at 5-4, and he's looking at a particular, in fact, very particular variant of the classical Ising model, right? So one of the things that I think it's getting back to abstract frameworks, it's a kind of model construction strategy in the background to pick a model construction strategy that works on one side and transfer it over to the other, right? But then it's happening at a more concrete level than that concrete framework level. So it would be a different kind of project as you would do in axiomatic QFT to say, okay, I have a QFT, let's construct models that are mathematical models of a QFT. But at the same time, actually, there's a way of seeing how that works here too. But I do think that one of the concrete model construction is something that is relevant as an application of thinking about abstract frameworks.
So there's something I feel like I don't think you said explicitly. So if I were to say that something, so formal analogies are hugely important to theory interpretation, right? Precisely because a lot of the time you know fundamental theories, theories. The fact that you have two layers of theory that are related by very similar mathematical techniques tells you a lot structurally about the theory. It does tells you feasibly something about how to interpret two bits of higher level theory. Similar. So there's a lot of interpretation. Feasibly, like you might not think it's not actually what different phenomena are alike in you might think there are other places where a lot about interpretation and ontology, precisely because you think that a lot of the time when you're doing interpretation, all we have is these kinds of structures. Is that something you're saying? That feels like that cuts against some of what you're saying.
Yeah.
It doesn't have to be said explicitly.
Well, right. Okay. So let me disagree with you then. Right. So, yeah. So why do I think we have to be careful about that black line? right? And often, like, if you're doing philosophy of physics, what do you have to go on to figure out, given a nice mathematical theory of some, mathematically stated theory of some type, what do you have to go on in order to figure out what the interpretation is, right? So I think that using analogies as a guide, you have to be incredibly careful about the heuristic role that some of the physical intuitions have when you carry them from one side to another. So spontaneous synchrony is a great example of this, right? That there's lots of sort of context-specific reasons why the BCS model of superconductivity was then the huge key to constructing the variants of the Higgs model, right? But one of the things that I think was the case was we have a physical intuition about what happens in superconductors and because there's phase transitions and you are intervening on this system that, and then you can change the temperature and you can do all these experiments and see what happens. And so there's physical intuitions about causes and effects that are of an interventionist kind of nature there. And I think that was hugely important in the heuristic step of then constructing the Higgs model mathematically. But what I think would be a mistake to take that and say, okay, now we understand what the Higgs boson is. It's the same kind of thing, right? But it's not the same kind of physical thing. It's a kind of mathematical representation that you've developed, and then I think you need to move on from that, right? And then take the Higgs model on its own and figure out what the Higgs model is telling you about the Higgs boson. The other strand of that was a kind of structural realism.
Yeah, structural realism is applied to kind of emergent.
Right. So I have a diagram for David here that people are pushing me to here, I think, at this point, which this takes me away from the main things I wanted to stress in the talk. But maybe I should ask David whether this is like close enough to what he thinks. So this is like a kind of like Wallace on QFTs and EFTs kind of redux, right? So what I have at the top are frameworks of some sort. David doesn't really distinguish between the concrete ones and the abstract ones. I assume there are some sort of like concrete frameworks. But what's important here is you're dividing things along the quantum classical line, right? And so, and then the EFTs come in because you have enough structure from quantum theory that you then, so I think a good, I didn't talk at all about quasi-particles, right, and particles, but I think that's something that's going to be quite different from the picture I had and this picture that David has, right? And this is going to play into like structural realist intuitions about how much you need to specify by way of content in order to get an initial grip on physical interpretation, right? And the more structural realist you are, especially I think in David's vein, the less you need in order to think that you have. And then of course we're going to disagree about whether that's the right way to be a realist or not. But so let me just put my diagram back and explain more what I have in mind here by the differences. So it's important to me that based on the examples I've looked at, so I have my black line between QFT and statistical mechanics. So my line is kind of a relativity, non-relativity line. It's not a quantum classical line. In fact, in a lot of the examples, it's kind of important that you have classical statistical mechanics thrown in here with quantum statistical mechanics, which is not to say they're the same thing, right? I mean, then you start like subdividing into different levels of concrete frameworks, but this is the way I'm dividing up frameworks. And so I think that there's different ways of dividing up frameworks. Obviously, the classical quantum theory divide is also an important way, and things get messed up in the 20th century, right? There's like a couple of different revolutions happening simultaneously. How we sort out those differences is still an ongoing kind of project. I mean, I think I would have reservations about putting QFT in that corner, for example. And now we're maybe getting into more specific details about disagreements about QFT in particular, right?
Yeah, I resist the temptation to abuse the chair to follow up on that. Just behind them. Sorry, I struggle to see you out from here. No, you're third next. So yes. Yeah. I have a bad line of sight on here. People next to Mark, and then right at the back, I think is Marion, and then just behind Mark, I can't see who the last is. Oh no, you're third. Yes.
Oh, that's an excellent question. Yes.
And I mean, the other thing is.
Okay, that is an excellent question. I think that's one of the really, like, that's the kind of question that I think having this abstract framework in view allows you to articulate clearly. So the question is, okay, so if we have, like, say, let's just make this simpler than renormalization group methods, which are kind of complicated. Let's say we have the wave equation, right? The wave equation is a piece of mathematics. We know we can apply that all over the place, right? So why is this, what I have up here, any different than that? Why shouldn't we just think you can have apply like some equation or something, like some fixed mathematical structure at the highest level, and then we just interpret it in different ways. So here renormalization group methods will come in as an example. So the reason why formal analogies need to be used is precisely because we don't have that fixed mathematical structure that we can then see and apply in different cases. So this is kind of the question I was trying to get at by talking about calculus versus the way in which renormalization group methods actually work on the ground. So on the ground, you don't have like the renormalization group transformation that you apply to different cases. So for example, you have, and see the paper that I wrote recently for more on this, you have semi-group versions, say, of the renormalization group transformations. You have full group transformations. They're different, right? You use them for different reasons, but this is kind of what I have in mind is you have a family resemblance between all these kinds of techniques that involve scaling and often limits of different kinds, but it's very important for practical applications that they're not actually like, it's not like one equation that you're applying all over the place. Yeah, so that's a good question.
Marianne.
Thanks, right? So my question touches on these couple of questions about interpretation. So take at which of these four levels of any one seems that are appropriate objects that you take a characteristic yellow is not the right level.
Right.
So you need to do it at the other three in different ways. What's the
Okay, so that's a great question. And so let me answer it this way. The main point I want to make is not the yellow level, right? As you said, that's the point. That's what I want to argue for is you haven't said enough about physical interpretation to be committed at that level. Say you're a scientific realist for whatever reason you like, right? If you're a scientific realist, it doesn't make sense to be a realist about the field framework. You have to go down, right? So that's the main point that I wanted to make. Maybe actually coming back to one of the earlier questions, that's important to me because then what level is the right level is going to depend on what kind of scientific realist you are, right? So, how far down you need to go is going to depend on what kinds of content that a theory specifies say that you're going to be committed to being approximately true, right? But the most important point I wanted to make is that I think questions of realism and anti-realism are kind of beside the point if you're at the top level, right? And this is kind of what I had in mind by saying, look, I'm not like, I don't think that there's any like big, like there's no pre-established harmony between this mathematical representation of the world because there's no representation of the world at all. So the world just actually doesn't come in at all, right? At the top level. So I'm not committed to any particular type of realism or anti-realism, and I think that I don't need to be to tell my stories informed.
Okay, so I've got just in front of Marion, your question. Yes. That's what you have to ask.
That's not a problem.
And that's, I mean, so there's no stronger physical qualification. Also, I don't know, but it's not very, so, talk about how two theories and mechanics, I don't know to say how similar, they aren't much in this time.
Okay, good. So computational neuroscience. All right. So yeah, that's another area in which like you use abstract sort of mathematical representations. So to be clear about some of the things I was saying about interventionists versus other types of causal explanations, all of that is going to be, it's going to hinge on like what kind of interpretation you give at the concrete level. So I think even in neuroscience, I think you're going to have to get down to some sort of, you have to say something about what the variables are representing, right? And so I have no, I think that there's cases in physics where you're not, it has nothing to do with causation, what you're doing, right? That's not a reason for, and that's not why your reason for applying the model has nothing to do with wanting any kind of causal explanation. So it would not surprise me if that's also the same in neuroscience, but of course I have no idea. But that's my answer.
Okay, so I've got John, then Jim, then Bob. Just give me 1 second.
Thank you very much. I just want to say you're right about the unreasonable effectiveness of mathematics. And let me just tell you why, because I think there's a way to make the case that's fairly strong. 2 points. First, it's based on bad history. The idea is that mathematicians come in with these perfectly formulated mathematical theories that then turn out to be true physically. It doesn't work that way. It's the opposite. What happens is a physicist makes some sort of discovery. It's mathematically a god-awful mess. The mathematicians come later and clean it up, and then it looks beautiful mathematically. It's been that way from the beginning. Just one example will suffice. Think of Newton in Principia. He's using Euclidean methods to do something that's really badly adapted to Euclidean methods. It's 100 years before you get the beautiful calculus textbooks that make Newton's analysis look pretty. So that's the first thing. Then the second thing is there's vastly more mathematics out there than's in the world. This is Shakespearean. There are many more things dreamt of in mathematics than are in the world, right? And so, of course, for any physical theory, there's going to be a mathematics that does the job. That's not anticipation of anything. It's a bit like going to a shoe store. You sit down, the clerk brings out a shoe, it fits your foot perfectly, and you're amazed. How did they know? Well, they've got a complete shelf in the back of the store with every possible size. You know, I think we've got to get rid of this idea that there's some kind of preordained harmony between mathematics and the world. It's highly contrived.
So I agree with your conclusion. I think we don't even need those other arguments, but yes. I mean, the reason I bring this up is because one of the arguments that's been given against purely formal analogies playing a useful role in physics goes back to Wigner, right? And being afraid that then you're stuck with something that's inexplicable by way of methodology. So I, first of all, don't think that the initial arguments are good, but I think that is something that you should be thinking about as a live worry if you're trying to defend, as I am, the purely formal analogies. But it makes it hard to write about because like you need a good argument to argue against, and then the real thing. But yeah.
Jim.
Yes. Thanks for the talk. This is sort of a continuation of Siddharth's question. I don't know to what extent I really entirely believe what I'm going to say, but let me just try to push you a little bit. And it has to do, again, with the sharpness of how sharp you think the distinction is between the purely formal analogy and physical similarities. Because after all, in one of your early slides, when you were describing something like the preconditions for the application of the field concept.
Right, exactly. That's what I was doing.
You described,
Yeah.
you know, physical features. There's something that sort of looks like points with degrees of freedom, correlations among them we're interested in. You could add other stuff, maybe the interactions are local or something like that. And so the question would be, even when you've done that, haven't you already described, admittedly in a very abstract way, sort of physical features that kind of underlie and kind of allow you to understand the applicability of mathematics. And in fact, if you want to answer Wigner's question in a naturalistic way, aren't you going to kind of inevitably end up saying something like, you know, what I'm now talking about, namely there are these, you know, physical similarities between these otherwise very, very different systems that, you know, explain why it is that we can use the same mathematics for both. And then finally, if you say that, why shouldn't you be a realist about even the abstract field framework? You know, there are certain features that are really out there in nature that you know, have to be present for the framework to be applicable. And with the applicability of the framework, we have good reason to think that the features are really out there in nature. I don't know to what extent I believe this.
So
but...
I mean, let's make it a little bit more specific. So let's make it a bit more specific though. Like, when you get specific, I think it's difficult to think about like how you would defend this view, right? So think, okay, so maybe you should be a realist about the abstract field framework. That means there really are degrees of freedom. But then I think the key there is that's telling you more about how you're choosing to model the system than it's telling you about the world, right? So,
well, the world is such that it allows itself to be, you know, modeled in this particular way, that there are such and such a number of degrees of freedom and so on. And that would be the way you would. You're not, it's like you're ontologically committed to there are things called degrees of freedom that are completely.
It's not just that they're, yeah, so it's not just that they're called degrees of freedom. It's more, so I agree with the first thing with what you started out with, right? Is basically what I was giving was, you can go back and read it, and even actually Ken Wilson's so brilliant on this. Like, go back and read his original papers, and he lays out what the conditions of applicability are for, and he talks about renormalization group methods as a kind of applied mathematical technique, in very much the way I did, right? Yeah, I mean, do you think they're really, there's some philosophers going to defend anything, so I won't even finish asking that question of myself, but I just like, by the time you get to that level, I just think, like, if you're a realist about that, right, like, that seems uninteresting, and I don't know that it plays any kind of interesting, like, explanatory role in explaining how anything works, but.
Oh. So maybe my question will provide a more concrete example of what Jim was trying to get at.
Okay.
So when, Schwinger and Martin wrote a bunch of papers, and Kadanoff and Martin wrote a bunch of papers about applying the field concept to many body systems, not quantum field theory. They're the idea that we could give a correlation function description of these many body systems and do a lot of work with that. Is that just a formal analogy between those two, or I mean, what's happening? It seems to me, along with Jim, and is that the world is in such a way that in fact there are these mesoscale correlations, and we need to focus on them in order to try to understand both behaviors of these different kinds of systems. It seems like there's a really deep analogy between the use of the field framework in both the quantum field theory case and in its matter case, and it seems doesn't seem to me to be merely.
So maybe I misunderstood the example, but the way when you were explaining it, I thought that the example was all over on this side of my black line. Is that not right?
No, so I don't think so. I mean, I believe that what Schwinger and Martin, and not Martin, that we can employ sort of the Green's functions techniques in field theory and provide correlation function descriptions of many body systems in the mathematics. That's a really tight analogy. And the reason we can do that is because the world just happens to be such that there are these mesoscale correlations to yield to in order to.
So I have to think more about the details of the case study. What I'm tempted to say now is that would be the kind of thing I would call a formal analogy. And so there are lots. So Green's functions is another like code name for a set of. Sorry. Green's functions. Sorry.
No, I didn't mean to interrupt. Sorry.
Yeah. Anyway, so our for another kind of for another. Then there's a set of mathematical tools you can use to calculate them under certain circumstances. So what I would say about that kind of example is that you're going to end up with I want to defend this fundamental divide on the two sides of the line. I think you're going to have huge classes, obviously, on the one side, on the statistical mechanical side, as you're thinking about like critical exponents and that kind of thing, right? You're going to end up with like huge classes of systems which are very physically different, right? Which end up in the same class. So that's all going to end up on one side of the line. But you are at a certain point going to have to, especially when you end up with methods that are only going to be applicable in certain circumstances, then yes, that's obviously, in order to say what the circumstances are, you need to be saying what's happening in the world, right? So then you're going to be sort of down, first on my diagram, going to be down somewhere here, right? So you're going to be recognizing the same sort of, like somehow some sort of similarity between all the circumstances and different physical circumstances and different physically interpreted theories or concrete frameworks or whatever. But
so I've got several people coming around again now, so I'll put myself in queue at this point.
I think it's fair enough for you to ask a question.
So there's a lot of questions I could ask. Let me pick one that came out from Eleanor's talk. I mean, I'm really interested by this idea that the split here is relativity versus analogies. I mean, the prima facie concern would be we do relativistic stat mech all the time. I mean, half of astrophysics is relativistic statistical mechanics. Black body radiation is relativistic statistical mechanics. There are relativistic phenomena in solid state physics in some cases where the electrons are sufficiently excited. So how do I reconcile that with the idea that the split puts stat mech on the NR side and not at all on the QFT side?
So I think you end up with a picture like this, right? When you're thinking about, the way you started out asking that question, you're thinking about different types of systems in the world, right? And whether we thought that they were the sorts of systems that would be in a regime where we need to take into account relativistic effects or not, right? So that way of carving things up focuses on what you think the phenomena are doing in the world. Whereas the way of carving things up I had in the previous slide was, okay, so what are the, like, are you using relativity at like a fundamental level in those frameworks or not? And that's how it's going down. So I think if you're thinking in terms of what the phenomena are, then this leads you to think in terms of like an effective field theory type of treatment of maybe using different representations at different levels to account for different features of even one type of phenomenon you're interested in, right? So like thinking about low energy QED, something like that, right?
So just as a concrete example, I mean, suppose I'll take a low temperature superconductor and I'll put it in a box, which is filled with radiation at a certain temperature, and I want to study how that system evolves. Now, the low temperature superconductor looks like it's on the right-hand side of your diagram, and the box of black body radiation looks like it's QED phenomenon on the left-hand side of the diagram.
So I don't have, okay, good. So this is maybe important to clarify. So I have theories. I have representations on my diagram. I don't have systems in the world, right? So if you instead are thinking, okay, well, I have a system in the world, I need to have some set representation, or more likely probably a set of representations to try and account for the phenomena I observe in my system in the world, then that's going to be a different kind of project, right? That's I'm trying to classify features of representations, and because I start at the top, and because I inserted these levels in the middle here, like how am I distinguishing those, right? That there are tons of different systems which, after you get down to far enough levels of nitty-gritty physical interpretation that are added, you can model using that basic framework as a starting point.
Okay.
Right.
So I think I just want to finish clearing. I mean, where on the diagram? Granted, these are bits of framework. The framework I want you to do to model black body radiation, is that on the left or the right?
Well, if you want a framework to do it, it depends on how much, it depends on how much you want everything to fit consistently together. I think if you want everything to fit consistently together, this is the kind of problem you're trying to have to solve at the concrete framework level.
Okay, fair enough. But then, I mean, I don't want to get to just to flag my concern now. I mean, black body radiation is not some esoteric phenomenon of the frontier of physics, as you know. It's I guess that's I should ask, when you say this is a project, do you mean that's a project for philosophers to understand or for physicists to do? It feels like for black body radiation, at least the project was done a long time ago.
Yeah. So I mean, it's a project for physicists to do, and I was telling a kind of historical story, right? I was talking about the beginnings, and so I think the formal analogies are particularly useful at the beginning when you're trying to when you have nothing at all to describe electroweak interactions, and then you need something, right? So then you get the Higgs mechanism and all of that. But then as philosophers, we're of course interested in what happens at the end of the story as well, right? And so this is the kind of question you're asking. And to me, what's interesting is to figure out how you get from the point at which I think this picture is quite a good picture for understanding what's going on to what we have now.
Okay, this is historically indexed.
Well, no, it's not historically indexed, right? But so I think one of the things, though, that could be useful at this stage is the field framework's not going to get you for free a unification of these two physical theories, right? Physical frameworks. But it could give you ideas, and this is what finite temperature field theory is all about, right? It's thinking about like what scattering looks like if you have heat reservoirs and stuff like that, right? We can talk a lot more about this.
Yeah, great. Okay, that's really helpful. Okay, okay, I've got Kabir, then actually I'll take Mark if you haven't asked a question yet. And then it's Kabir, then Siddharth, then John.
So you've said that you have to assume to have physical unification on the field. Suppose that I want to value that we actually have physical unification in a particular field. I would value that. Is it possible to do that? What would the conditions need to be on this additional physical unification?
So are you saying, is it possible to have models maybe at the lowest level, or like even theories say, that don't fit on my diagram? Yeah, and yeah, I think it is, right? Because one of the big projects, presumably in physics, is we have to start somewhere. So usually where we start is by trying to figure out how to model appropriately particular types of systems, which might have some relativistic property. In certain regimes behave relativistically, in certain regimes maybe they don't. So that would be something that would be requiring a lot more physical interpretation. So I think, yeah, we're going to have, and we presumably do right now, actually have models and theories which are not going to fit on this diagram. But then the question is, like, where do we, like, how high can we get? How general are our physical theories which apply to these models where we've been able to get traction at some, for some specific kinds of phenomena in specific circumstances?
Thank you
so much. Yeah, well, it's quite good that you have this like. My question was, it's more of a clarification. Can your view account for concrete frameworks which might have more than one abstract framework? That you can...
that's a great, yeah. So, yes. I mean, I think the field framework is very widely applicable, so it's a really nice illustration. But I think, yeah, there are different like abstract frameworks.
So I was just thinking that, say fluid mechanics. So you can do lots of good stuff. It's just fluid mechanics without even talking about fields. You can maybe just talk about particles or something. So there is at least a certain fragment of the concrete framework which has nothing to do with the field framework.
Sure. Yeah.
So you can have like 3 or I don't know more than one arrow
from the top. Yeah.
Coming into a field framework.
Sure. Yeah.
Okay. But when I'll just stop there. But would that create any problems about for talking about formal analogies? Because then we can't maybe go straight forwardly from QFT to statistical mechanics and say there's an analogy, because you can say, oh well, I don't know if it's going through the field framework or if.
So actually, I think the opposite. One of the great things about analogies is between any two representations, you can pick out different sets of analogies which are mutually inconsistent as sets, right? So as long as you pick a set of analogical mappings, which is internally consistent as a set, then there's lots of ways in which things are similar, right, along different dimensions of analysis. So that's, I think, actually one of the cool things about analogies.
Siddharth. Oh, actually, sorry, Mark. I'll take you have the question first.
I agree. I agree with you on most of these things. I would add, when we talk about field, the actual productive amount is shared from field and the symbol. So, and then the other thing about fields is it's a class of this word class. It's a classic lesson green on ocean. That field real analysis of distributed is where you find clues to reliable calculation. So sometimes you want contentious physics in a complex field with unreadings. This classical elasticity, you want to use a complex field. You get the best mathematics and a visual signpost of how to reason. What I want to get, this is a quote from Kelvin too. They use fields of the right. And they say, well, in appealing to these, we are letting nature do calculation, so we can't, but that ability to move, to make a bridge, and get a dependency in nature, they would certainly resist practical mathematics. Even when it can make sense of it. I mean, the 19th century was very careful about limits. Did the errors. And a lot of times you'll borrow some field that's in effect something like the central limit theory, but you don't know. But so the field is very important. This was uniform. Very well in that.
Yeah, so I like that quote, by the way. That's nice. And I think one of the things I've been thinking about is I do think that there is a change that happens between the 19th century and the 20th century, and trying to be clear about what I think is different, right? So as you were just saying, that there were fields is obviously something that goes back in, very important in 19th century physics as well, right? Before I had my diagram at all on the first couple slides. I think one of the differences between how, like, say, Maxwell and Calvin were using analogies in electromagnetism and the types of examples I'm looking at is that at the end of the day, of course, getting Lagrangian mechanics and analytical mechanics, as you know, so that it could be really useful and to get electromagnetism in that framework took a long time, right? But once you get to that point, you can look backwards and say, okay, we can give an account of why those analogies, why those analogies worked. That is highlighting the role of formal field framework, but also the dynamics is important, right? And so you can give an abstract characterization of the dynamics that they're using that has physical content to it. So I think that's one way in which what's happening in some of the examples in the 20th century is you're mapping sort of the Lagrangian to the Hamiltonian. So that's why things get kind of mismatched. So that's not directly relevant to what you said, but I've been also thinking about it. So, but just to say, I think that part of the story here I left out is what you make of the connection between what's happening in the 19th century and what's happening in part of the story I was focusing on.
Yeah, but Siddharth and then John, and that's probably all we have time for.
So how much do you, let's just maybe a bit of a nitpick, but how much are you actually hanging on the sort of bubbles up there, the closest coincident time?
Oh,
because you can
that's not going to be general.
Okay.
I think for the examples I've looked at, that's part of the heuristic story of why those analogies are useful. It's interesting, but I'm not going to stick to that as being like, I don't think that quantum field theory is the exclusive domain of dynamical representations or anything like that.
This is sort of a weird question. You're doing a terrific job of answering, but I'm not following the questions. I'm hoping you can explain them to me. I look at this figure here, On the right-hand side, I see an Ising model, which is going to typically implemented in fermionic matter. On the left-hand side, there's a phi to the 4 model, which is a bosonic field, right? And then you point out that there are mathematical similarities that turn out to be enormously useful, and that seems terrific. But then I hear talk of there's a deeper connection, realism comes in here. And I'm trying to figure out, what are you being asked? Yeah, there's a connection between them. It's exactly the mathematics that you've just described. I haven't been able to follow the questions. Can you? But you've answered them.
I think that, like, if you think of things in this way, I can't explain people's questions.
Why does the math work? Is one way.
Why does the math work? Is why. I think if you carve things up in different ways, then you're going to have a lot more physical content, like say on this picture between the bubbles, right? Or maybe David's picture is a better one for this purpose, right?
But Jim just put it nicely. He said, "Why does the math work?"
Yeah.
What counts as an answer to that question? It sounds like one of these weird philosopher's questions. You don't know how to answer it.
Well, I mean, why can't the answer just be that there are these certain, rather abstract physical similarities between systems that, in more specific ways, are extremely different.
But what's different between that and what you just said? There's a
I think that's
well, because if you just said, I don't know, I'm just talking off the top of my head. If you just say there's a mathematical relation, to me that seems kind of mysterious. I want to understand why it is that you can do this. You can take this bit of mathematics here and apply it over there.
Yeah, I'd flip it. What isn't mysterious is that there's a mathematical relationship. What is mysterious is what will be needed to answer the why question.
So maybe let me take another stab at your question, Jim. Just like 2 sentences, and then I'm done here because it's time for reception. So I think the types of questions you're asking are best answered at these lower levels, right? When you're asking about like why, what are the like conditions of applicability in the world of a particular bit of mathematics, are precisely the ones where you're going to need to have to be able to, and maybe this is somewhat related to Bob's question too, right? That if you want to say, if you want a deeper explanation of why the math works, then you're asking for conditions of applicability, which can only be stated and made out when you get down to a certain level in my scheme.
I think we could
Yes, we can keep talking about this. I'm happy to.
I think we could keep the discussion going for another hour easily. I think we should give Doreen a break at this point. So let's thank her again. I think we have the reception just next door in the appositely named Adolf Grunwald.
So I'm coming to dinner. We just made it at 6:30.
I was going to gather people up to about 6:25 or 6:20. If you want to.
No.
Because I want to know why so many systems in the world follow approximately Gaussian. I don't talk
Right.
specific stuff. I talk
So that's a
about,
good example.
well, I talk about, there's an additive sum of a bunch of individual random variables that are independent of one another, and they have finite variances, and that's a distribution by the central limit, and that gives me a distribution that's Gaussian. So it seems to me the explanation for why so many systems are Gaussian, and that's the sort of thing I'm
It sounds like
talking
the
about.
first thing you said, that I think, oh yes, that sounds like what I'm trying to say as well, right? And so I guess the disagreement is about whether that's providing a physical explanation or not.
What
A physical explanation, or is that?
Yeah, well, I guess I do think it's because it is just stuff in the world. It's a fact about the world that these variables that you're adding up
I understand
And so-
what's
and
being
then-
said. I try to make
so-
it precise. I'm still stuck.
Yeah,
with
I can see
the
what you're saying, because I also don't want to,
Analogy is
I think it's
just been
important
said,
that
right? I mean, the different.
sort of abstract representation
Mechanism is in the
I
center
don't
of
want to get into a very
strong
concrete
whereas the conductivity lives elsewhere, right?
physics come in, right? Yeah. Yeah.
This was a fascinating talk. I mean, it's a lot of really. Have you written about this? I don't know, when you say interventionist explanations, do you
So,
have anything like what some of us who use that language?
so, what I was thinking of was, mostly if we look at the cases, so I think that spontaneous energy breaking one's a really good one. In that, to me, it seemed, looking at what happened historically, it was absolutely crucial that you could, temperature is an external variable, right? And you can intervene on the superconductors. And so then, like,
We should ask her, but I didn't hear her say that.
you can do measurements, right, to see what's happening with masses.
So because there are physical analogies, and that seems.
Fine with me.
It's a little unclear exactly.
I have to go.
But so I'm writing about this, and so this talk is like,
How we
have all these
exactly define it was in
examples,
principle.
case studies
everything
worked out, and this talk is supposed to be the
So.
prologue to the section with all the examples that I'm trying to.
Well, I'm certainly very interested. The contrast you want to draw.
Yeah.
The latter, I take it, not being susceptible to.
Right, yeah, so then you're gonna, yeah, and so this is, yeah.
Yeah, there's, I mean, no potential.
You got it.
That was all.
You're coming to do it.
Equilibrium log.
No, my partner is flying it that weekend, and she just landed.
Evolutionary.
You're more afraid of offending your partner than of.
Thanks, yeah.
The answer is yes. The answer is yes, and that's the correct
I
answer.
was gonna say, I'm still new here, so I'm not sure if that's the correct answer, but that is the truth.
I can tell you right now, it's a correct answer.
So I need to turn this
I
off.
got the, when I first got the hot, I got the. I first got the.
You're the engineer, you should be able to.
I just looked at the switches. Oh, there it is. It's on the side. I got the departmental nickname. I have no idea. It's not turning off for me.
I couldn't see a button which would,
No,
like,
no, I can
it sounded
see-
like it turned off.
Look, that's a button.
Oh, it sounded like it turned off.
It doesn't seem to do anything though. So I got the departmental nickname went for exactly that reason. Because they said, let's all go and drink, and I said, no, I'm gonna go.
Yeah, we're not living together right now, so she's just coming in just for the weekend. I figure I should probably, she made the effort to come here, I should leave.
I've spent a lot of time with Adam over the past 2 years, so it's okay.
Sorry?
I spent a lot of time with Adam over the past 2 years.
Oh, that's it.
He was
Oh,
my
that's it.
postdoc for the last 2 years, so.
And we had coffee or something.
Oh, hey, I was just wondering if you're not too tired for more questions.
Yeah, I'm gonna grab something.
Yeah.
And I'm gonna put my computer away, and then I'm happy to chat more.
Great job. by the way.
Oh, thank you.
It's very helpful for me to think about things along the similar line.
Do you think we should end this?
I guess so. Yeah, I think we can just, no one's gotta be here. So